Bom dia. So I'm happy to be here. And what I want to do today is to combine some very practical talk where I want to show a couple of applications, at least on PowerPoint, some of you can, that you can check out on the web, with some fundamental considerations of what is happening under the hood, even from very deep philosophical history that happened and that sort of like influenced computer science, and then try to show you how these two different lines of thought converge in the semantic web and in a very practical approach towards the semantic web. First, when I talk here about explicit and implicit semantics, I have, of course, to talk about what does it mean? What does explicit and implicit semantics mean? What does semantics mean? Are you well aware of what semantics means? And by the way, when you have any kind of questions during the talk, just raise your hand and put forward your questions so we can have it a little bit more interactively. So, do you have a good idea of what semantics is? Are you bothered by semantics in your, let's say, life as a computer science student, which I guess most of you are? Yeah, absolutely, right? Because you communicate. And you communicate either with your peers, right? Then you use Portuguese, English, whatever kind of language you prefer. And with saying sentences, you convey some meaning to the other person. And as a developer, as a programmer, what you write down are sentences to the computer that the computer is supposed to understand. And, well, obviously, especially in computer science, we deal a lot with syntax. Which kind of words can we put to which other kind of words? Which kind of operators can we put to which other kind of operators? But then we also need a good model in our head what these operators mean if you put them next to each other. And semantics is about understanding how these different words, how these different operators, how these different sentences work. We have this layer of syntax where we say what are the allowed sentences. What are the allowed sentences of the Java language? That does not tell us yet what is the meaning if we code a particular line of Java. And describing what a particular line of Java means is what the semantics is about. Now, I will not go so much into programming language semantics here, but rather I'm more interested in data. And I'm interested to analyze data coming from all different kinds of data sources and coming also from huge data sources. And then the question is, what is the meaning of that data? Now, if we have such large data sources, then why do we need semantics? Well, why do we need to consider it explicitly? Well, of course, we can then ask questions, if you have semantics, like what are the most important Greek philosophers? And hopefully we might get an answer like that. Like seeing some picture or some statue of Socrates, of Plato, of Aristoteles. And where is the semantics here? We need to understand the semantics of these images in order to be able to answer this question. Sorry. We must understand what this sentence here means in order to give these kind of answers. And we must understand what is depicted on these images. Otherwise, we cannot give this answer in a meaningful way. Or, other example, we may ask what are best-known Portuguese authors? And maybe we want to come up with a list of such authors. I mean, maybe even just by looking up Wikipedia, because there we have already quite some structure, quite some authors in there. And then, of course, it's still a question, are these really the best-known authors in the Portuguese language, right? Maybe some of them are rather unknown and just inserted by their own children or by themselves. So we need semantics in order to understand our data, our images, or our words, or lists of authors, in order to come up with answers to what are important philosophers, what are authors that are also Portuguese. Now, if you look at explicit semantics, then what is happening here, the whole idea of explicit semantics, you can say, can be traced back to ancient philosophy, where people like Aristotle invented logics. So he, in his organon, for example, described syllogisms. What is a syllogism? Well, he describes a certain figure for concluding facts from other facts. What would be such a kind of combination? Well, it could be a kind of a rule, like every man is mortal, and a fact like Socrates is a man, so we can conclude Socrates is mortal. So, and he described a couple of these syllogisms, ways in which we can reason with this kind of language, even if we do not know what Socrates refers to. And maybe I should have put up here the image of Socrates, the cat from this cartoon, so you understand that it's not automatically the Socrates, the philosopher, that we talk about when we use the word Socrates, but it could be a cat. And if we say that this cat is a man and every man is mortal, we would also have to infer that this cat would be mortal. When you look at the structure of the syllogism, you find that not all the words have the same kind of status. Some of these words are rather like concepts, like, for example, author. Author here in general does not stand for a particular person. It's not an individual. It's rather a whole class of entities. While then you may have other entities, like Socrates or Saramago, and there you really talk about a particular entity, an entity which is a member of the list of authors, for example. And philosophy also gave us this idea that when we describe the world, we describe the facts, we describe the rules, we can really sort of describe everything that is of matter to us and that we communicate in our language. So this line of thought comes, among others, from Wittgenstein in his Tractatus Logico Philosophicus, where he said, when we talk about something, we can talk clearly about it, and we can describe what are the facts, what are the rules, what are the logical connections between different facts and rules. And if we don't talk clearly, we don't need to talk. Right? So, and that's, of course, very nice if you think of computer science programs, because when you program the computer, you are very precise, or you cannot really program the computer, because he will not take away from you the burden of understanding. You have to tell the computer what you want to achieve. So, in a way, you can say this extremely brief abstract of logics invented by the philosophers from Aristotle to Wittgenstein in the early 20th century gives you this very idea that we can structure the things that we talk about into individuals and into classes, and that we can talk then about these individuals and these classes in a meaningful way, and all that we want to communicate and be able to communicate, we can express very clearly with the kind of logics that they gave us. Now, when I say with the logics they gave us, the philosophers were first concerned with sort of natural ways of writing down facts. And we're not used to that in computer science anymore. In computer science, we often have logical operators, and we use them independently from whether there's a natural meaning to them. One example would be a non-piano. So we take the concept of a piano, and then we negate it. And in first-order predicate logics that you may have encountered in your studies, the meaning of that is very clear. It's everything which is not a piano. But you would not talk about your girlfriend, your boyfriend, in terms of he or she is a non-piano, right? It's not really the way that we talk. That's not really the way you describe things. When you talk about a natural kind of logics, what you really do is you always contextualize that. And the notion of a non-piano may make sense when you talk about an orchestra, right? And then you may consider all the instruments that are not a piano to be non-piano instruments. That makes sense in a certain closed kind of context, but you would not talk about living people as non-pianos, right? So this original line of thought from Frege from the 19th century, Russell on the verge between the 19th and 20th century, they were more like into natural meaning and logics to describe the natural meaning of sentences. A little bit later, there came Tarski and Kripke and said, oh, I don't care about that. all that we care about is that stuff what we now learn in computer science when we learn logics, which is really that we say we write some predicate logic expressions. We don't care about what kind of symbols we use. And then we do interpretations. And then if we say all the x that are not a piano, we don't care about whether that's a natural set of entities to have or not. The only thing that we care about is that we can give a meaningful, very abstract, very mathematical interpretation to it. And that's a very powerful way of thinking about this mathematical subject of logics, which has given us a lot of traction also in computer science. But it's not very close to the original way of thinking about how to describe the world. And actually, when we do data engineering, when we do artificial intelligence, that's very often what we want to do. We want to describe the world on our computer in a way that's very natural for us, because we want to have facts about the world in our database or in our knowledge base. And we want to query this database and this knowledge base and get back answers that are natural for us. Well, we are at this point, when we're using this database or this knowledge base, we are not so much interested in quite esoteric thoughts that we could ask if we were mathematicians or pure philosophers, but we really are interested in very natural answers for our practical questions. And from this point of departure, we have also a history of semantics. I now put library science here under computer science. Now, of course, if there's any librarian in the room, I want to apologize already here because they will hit me on the head. But of course, they have looked quite a lot into how to describe the semantics of particular entities, namely of books and media. And by doing so, they have not only looked at the semantics of books and media, they also have looked into how to describe the things that are talked about in books or media or other kind of objects. And what is talked about in books and other kind of objects? Everything. So they have looked basically at how to describe meaning, very complex meanings. So librarians describe, for example, a book that has pictures about how to raise snakes for breeding them and giving them to zoo animals, right? So you have descriptions in the library science where you can express very complex concepts like these books that have images of snakes that are breeded in order to feed zoo animals. It's a really complex concept, and it's really semantically difficult to understand, but you can do that with the kind of structures they have. And they came up with thesauri in order to do that. For example, some of you may know the Dewey Decimal System, where you can compose concepts in such a way. They had not really looked at logics. They sort of like had a really somewhat ad hoc approach, which has some problems though, but which has a rich history and a rich set of descriptions that is still actively used in the libraries, of course. Now, computer science may be a bit more familiar to you, and especially if we talk about data engineering, because we talk a lot about individuals, or entities we sometimes call them, and classes or entity types in data modeling approaches like ER diagrams or UML class diagrams, and I have an example a slide later, or about classes in programming languages. All these we use in order to structure our world, and we use them in order to come up with an explicit semantics for the facts that we have in our database or our knowledge base. Yeah, and if you know the one thing, you know UML diagrams, but not ER diagrams or vice versa, just take the one for the other. That's good enough for this talk. And while these kind of approaches were mostly targeted by people who were from programming, for example, if you think of UML initially did not have a formal semantics at all. but it was used to structure the world in a meaningful way so people would know what they talk about when they write down a diagram with certain arrows and boxes. And the idea was that with these arrows and boxes, we can communicate clearly from one developer to the other developer, or we can produce from one diagram code fragments for our software development. So again, what we have to deal with here in these kind of descriptions is two kind of semantics. The semantics where we describe, for example, what a piano is or what an author is, to translate this into our programming environment. And we have to describe the semantics of the kind of boxes and arrows that we use in order to write this down. And of course, we have in computer science logics, which has migrated from mathematics almost completely into computer science. And we have the predicate logics, model theory. And we have, somewhat recently, a turn back in logics from somewhat arbitrary logical constructs to a more natural logics, where we try to talk about concepts that we use as people. So here is a very simple example you may have seen in the database class or data engineering class, entity relationship diagram. You talk about the class of authors on the left, the class of books on the right, and obviously authors are defined by writing books. So that's a very simple connection that you have here. And then you have some more attributes about authors and books, and you derive your database schema from that. And you may even go a bit further, and you may have an ontology where you not only describe the structure, but where you say every person who writes at least one book is an author. So you can do inferences in more directions than just by having tables where you say, I now describe authors in my specific database table. Okay, what have I shown to you now? I've shown to you, okay, we need semantics in order to ask meaningful questions for important Greek philosophers or for important Portuguese writers. And I've shown you a bit that philosophers have thought about how to think about facts and how to think about classes. And this kind of thinking, for example, here, about man and man being mortal, has actually also been done in computer science, where we describe things like man or piano or author as part of libraries, as part of data descriptions, or when we do logics as part of ontologies, where we describe how facts are connected in our world, how data is connected in our world. And here's just a very concrete example. Now, there have been innumerable many approaches in AI, for example, to build very rich systems. And maybe the most successful ones in terms of scope, in terms of breadth, have been done in the medical informatics. So if you think of UMLS, that's a Unified Medical Language System, and they have looked at talking about the medical world, and for this they have compiled this system called UMLS with a description of more than 1 million concepts. So what is a concept in this medical world? Well, the concept that you have are anatomical concepts. You have things like every part of your body, from the head to the toes to your liver, to a liver cell, to even certain caves in your head that everyone has. These are all anatomical constructs that are described with more than 100,000 concepts in UMLS, in a part of UMLS. But in UMLS, you will not only have the anatomy, but you also have processes. How do you treat a patient? You also have symptoms. What kind of problems may a person have, right? Some irritation of the skin or some wrong heartbeat. You have also descriptions of drugs and what kind of elements they may have, substances. And you may also have descriptions of treatments. So basically, you have 1 million concepts, more than 1 million concepts in UMLS to describe almost all of medicine. When I say almost all, one must also add this system is never complete, because as the medical world progresses, you discover that there's a new illness that you were not aware before, or that what you thought was one illness, one disease, is actually two illnesses, two diseases. So you have very large systems here. But these systems, one must also say, they have been built over several decades and by a lot of people. So for medicine, that was considered worthwhile because it's such an important area for our life. And so there was a lot of funding going into building these huge systems describing what happens there. In general, what one found, however, is that if we don't go into such a fundamental area, we have the problem that we want to describe data, but it's very expensive to do so. It was very expensive for the medical world. It's very hard to scale. You easily fail when you just want to describe comprehensively such a thing as a university. It seems like trivial to start to describe a university, but once you go even into a single course of study and you describe all the rules that apply in a single course of study, and then you imagine a university like this here has hundreds of programs, it gets really complicated, and when you're finished, the rules have changed and you start anew. So it's basically impossible to produce a description of all the data that concerns students here on this campus or another campus to put this into one system. The maintainability is just very, very low. And this kind of observation has been done for these kind of systems like semantic networks or for expert systems. It has been done in other areas like in data modeling. In the 1980s, people have thought about company-wide data descriptions. They wanted to have one large entity relationship diagram for a whole of a large company like IBM or any other large company you name. And the problem they always had was once they were finished describing the data for this company, the company would have changed. And the whole description that would describe all the data, would describe all the company, would not apply anymore. Because you can imagine, if you have a major company, that restructures itself after probably 2 or 3 years in a major way. And then all the descriptions you had before don't apply completely anymore. And you don't quite know where to start to do your changes. So what you have here is a lot of description of explicit semantics of data, but it's hard to scale, it's very expensive, it's hard to maintain. So let me talk about implicit semantics. Are you aware of implicit semantics that you use? People rather would say no. Well, when we now communicate, most of what I say, I have not given any formal definition to you other than maybe the initial definition of semantics. So when I use certain words, you don't know these words from formal definitions. You don't know them because I have defined, my name is Steffen, I'm a person, person falls into the category of living beings falls into the category of physical objects. I have not given this kind of explicit semantics to you. Yet from your experience, and from your experience of understanding the words that I use, you get a somewhat okayish picture of what I want to convey. So that's what implicit semantics is about. It's that you understand what I tell you, even if what I give you is not based on formal definitions. When we talked about this other line of thought here, when we talk about UMLS, these are all formal definitions. They're not necessarily all formal definitions in the sense of logics. So actually, you can use logics as a very valuable tool there. Yeah, actually, I can give you one nice example. It was about the female breast. My PhD advisor looked at the definitions of anatomy in UMLS and used some formal semantics to analyze structures. And what he and some medical people found was that the female left breast was modeled differently than the female right breast. There was no anatomical reason for that. Yeah, it's basically one is on the left, the other is on the right. That was the only real distinction, but we're modeled in different ways. So there was an inconsistency in the system just because it's so big and so hard to oversee. So implicit semantics draws on the idea that it's basically impossible to formally define all the words that are used, and to do this in a very minimal way. And one of the important protagonists for that was actually the same Wittgenstein, who first wrote about formal definitions about describing the world. So that's why it's often called Wittgenstein II. It's like his second major book, his first major book, was his PhD thesis, where he described how to formally analyze what we say. And in his second book, he basically said, that's nonsense. That's not how semantics really works. Semantic really works by looking at how we use language, not by formal definitions. So Reichenbach gave a nice example, namely, he asked the question, what is a chair? Okay, I ask you, what is a chair? How do you describe a chair? 4 legs. You sit on it. Other descriptions for chairs? Okay, you can, of course, do some Google image search. And so here are some chairs that you come up with. So this is hard to sit on. Yeah. Most of these don't have 4 legs, obviously. And so it's really, and for some, I'm not quite sure whether there are chairs. So is this a chair? From some point of view, yes. Maybe from some other point, no. This is something that you can sit on. Is this a chair? Maybe, I don't quite know. So it's not quite clear what makes it a chair. And when you formally describe what a chair is, then you may have a problem, because almost no definition would fit onto this collection of chairs. Right? So we have a certain issue here. Linguists have also looked at that, and they came up with this observation that they said, you shall know a word by the company it keeps. There was this other saying before, you know a person by the friends he has or so. You shall know a word by the company it keeps. So what is the mechanism that you observe? You observe this, for example, in search engines. Right? They take all the text, for example, that they find on the web, and then they look at what kind of words occur together. And from that, they draw inferences to give you a good search result. So you can, for example, ask for Lisboa, and then you find in, for example, here, Google autocompletion suggestions for what Lisboa may be. Okay, here, Lisboa Linda is maybe a very nice one. Some other ones may be a bit more esoteric. Well, of course, what is Lisboa without Benfica? And I'm not quite sure. I was not aware that the Estoril Film Festival was so important to define Lisbon, as it is assumed here by the co-occurrence of words together with Lisboa. And well, some others, of course, also make sense. Vale de Tejo. Sorry, I pronounced this all in the wrong way, but I guess you understand what I want to say. So what the search engine offers to you here is an implicit semantics. It offers to you this understanding of what Lisboa is. For example, that it is in a certain geographical location. That, well, I guess Lisbon is not the newest town after this destruction that occurred in the, I think, 18th century. And of course, it has to do with soccer, and of course, it's very beautiful. So you have an implicit description of what Lisbon is. At the same time, and of course, you could continue the list, right? So Google cuts it off here at 5 collocations. You could look into a large list. it may still be quite difficult to rule out other places that may be nearby, right? That are maybe suburbs of Lisbon. And of course, what you can also do then from such a kind of analysis, you can look at a text. Yeah, so quite a while ago, we looked at texts about hotels and tourism. And then you find a sentence like, you can book the hotel and rent a car, and you have much more sentences where you do an analysis. And for example, what you can do is you can come up with a list of words like hotel, apartment, car, bike, excursion, trip. And you can do a tick when a certain word co-occurs together. For example, book the hotel. So you could say, well, if you have a verb and book the hotel, so it means that this object, the hotel, is bookable. So in the corresponding column, you do a tick for saying hotels are bookable. But you can also book an apartment, you can book a car, book a bike, book an excursion, or book a trip. And similarly, you can rent an apartment. It's a little bit strange to say you rent a trip, and the same for driving. Some of the verbs are applicable for some of the nouns. And putting verbs and nouns next to each other is just one example. You can put also nouns together with nouns or adjectives together with nouns, and so on and so forth. And I think what you understand here is by looking at these kind of collocations, you come up with structure. You have an implicit semantics, and this implicit semantics tells you, for example, stuff about what is more general than some other thing. And you can even derive a hierarchy like this. You can derive from analyzing this kind of matrix what is a more general concept. For example, you could say things that are bookable is describe a larger set of entities than things that are rentable or than things that are drivable. And you would find that somehow car and bike must be somewhat close to each other. I'm not sure you would, maybe the driving a bike would just come from non-native English speakers, but these would be more closer together than, let's say, a car and a trip. So you can find structure just by looking at how words co-occur in text, or by, of course, listening to someone speaking and understanding how he uses words in a certain context. And it's not quite a perfect description, right? Because when you do this at a large scale, you find that a lot of words appear with a lot of words together. And also, if you apply this to a chair, you can do a lot of things to a chair. Of course, you can sit on a chair. You can also throw a chair. So maybe it's not very natural that chairs are thrown across the room, right? So you may have funny observations that may not really be so important for the semantics of a chair, for example. Okay, so what did I tell you about the two types of the semantics? We have on the one side the explicit semantics. It has a rich history in philosophy where people thought about how can we look at the world, how can we reason about the world, how can we describe the world. And they made up logics in order to do this. They made up logics more than 2,000 years before computer science came up, and these logics could be used to actually do something in an automatic way for us, just because they were interested in how does the human mind work and how does language work. What they did was to have a rather precise model. Every man is mortal. It does not really allow for exceptions, for example, right? Every bird flies. Well, there are some exceptions of birds that don't fly. So the idea behind these kind of models is that it's very explicit about what can be done and what cannot be done. And it's mostly very precise. It's mostly comparatively small when you start to write it down, because it's so really difficult to write down every aspect of what you're interested in a particular domain. If you have a very specific domain, then it's very easy. If you want to have a database of names who appear in a certain lecture, that's easier. You need the title of the lecture, a lecture number, the names of the people, maybe some people ID. You have 4 columns, you have a database table, you are happy and produce what some teacher needs to have for you, right? And you model the world in a very limited way. Once you leave this very limited world and you want to talk about what is a lecture and what may occur in a lecture and what has occurred in a lecture, it becomes very complex. And it's very hard to stop writing down this kind of model. So these models are mostly very small. And they mostly apply only to very small groups. So if you have databases about students attending lectures, they look differently in Koblenz, where I come from, than in Lisbon, and differently in Portland and in other places. Someone might say, why do they look so differently? It's always students visiting a lecture. But there's always a sort of nuance, a different aspect that goes into the description of these explicit semantics. But it's very precise. When we look at implicit semantics, we try to derive these implicit semantics from observations, from observing how we use language, for example, from how I put words together, from how I put words next to images, right? So if you want to teach someone who has slept for the last 200 years what a mobile phone is, even if you can speak rudimentary English and you say this is a mobile phone, he may not fully understand what the mobile phone is about, but by saying this is a mobile phone, he will understand. So it's about observations, and then you derive from these observations that certain things go together. You observe that you can sit on a chair, for example. It's very imprecise. These kind of observations can be huge. You may have to observe the web in order to understand what the words of the English language mean. And it's still not necessarily complete. So a colleague from England, he looked into specific domains like bioinformatics and tried to infer the semantics of bioinformatics terms from looking at the web and at documents about bioinformatics. And he found that most of the things he wanted to store in his database, he just could not observe on the web, in spite of the fact that the web is so huge. Specialized domain is not nicely captured just by looking at this structure. So I have to change this. Okay. And when we compare the two sides, we find that the one side is really good for programming, the explicit semantics. We can really easily come up with a small database and program against a small database. It's much worse for really large domains because we have this so-called knowledge acquisition bottleneck. It's difficult to fully capture a domain. Another example, we once were cooperating with a company, and that company built software for transplant patients. So patients who get a new heart or a new liver or something like that. And because they have these transplants, they build up a huge medical record because they need to take drugs such that their body does not repel the new organ. And because of that, they build up a huge record that grows over the years and has many dimensions because it affects the blood system, the nervous system, the immune system, and they have to take a complex cocktail of drugs. They, just for this kind of patients for transplants, they came up with a database of 10,000 columns. And it's a small domain. So it's a nice domain for programming, but still very, very limited in what you can do with it. And on the other side, you have implicit semantics, which is good for some open domain like search on the web, but it's pretty bad for actionable knowledge. I mean, who of you would say I do a web search and the best result I automatically feed into my robot such that he does something for me like booking an expensive trip. Right? I mean, I guess no one would dare to do this right now, to invest this kind of money. While here, you might actually do it to some extent. Right? You can have, if you have a decent combination of different data sources, you can have a complete trip from Koblenz to Lisbon, and maybe you give a cap of a certain limit that you want to spend, and you can program that. It's basically impossible to do this here. But of course, you want to have both. You want to have a really huge domain like understanding of life, booking trips for you in a really open setting, and then really also doing this kind of action. And the problem there really is that you have to grapple with these two dimensions that your explicit semantics you can never write down on your own or in a small group, but the implicit semantics really is not of high enough quality. Now, I want to talk about the semantic web and how in the semantic web you have both explicit and implicit semantics together. And as I describe this is not there that I can suggest to you solutions. It's rather that I say, here is an interesting problem. Go solve some parts of it and found a company that will become really successful, or build an academic career on it, because there are so many opportunities that are currently untapped. Now, who of you knows the semantic web? Oh, 2 people. Okay, that's good. So that's good because I have introductory slides for the semantic web. And I typically introduce this very briefly and with a somewhat artificial scenario, which is actually not completely artificial. So I always start to explain what the semantic web is by first explaining what the web is. And who of you knows what the web is? Already 4, 5, 6, 7, 8 people, more. So it seems like every second person in the room at least knows what the web is, and the other ones have to ask your peers. So what is the web? So if you talk about the history of the web, it happened that around 1989, Tim Berners-Lee had this idea, or had this problem. First, there was this problem. And I described the problem now in a little bit artificial way. It's not literally true, so don't say Steffen has said that was the exact truth. But it's simplifying the scenario a bit to make it a bit more expressive and easier to understand. So Tim Berners-Lee was working at CERN. CERN is this huge research facility in the Swiss Alps where they let collide particles against each other. And it's a huge ring where these particles are accelerated and then they bump into each other, and then they have huge detectors several floors high that observe what kind of reactions follows from that. Now, the interesting thing about CERN from my point of view is not that they have these particle detectors there, which I find a bit boring actually, but that it's a huge social experiment. And what is a social experiment? It's that physicists from all over the world, physics professors, researchers, go there, work for a couple of weeks, do their kind of research, and then go back home to the University of Koblenz, Karlsruhe, Portland, wherever they come from. And a couple of thousand people work there, and there's a large flux of people coming, staying there for a couple of weeks, leaving again, and so on and so forth. And what is the problem with that? Well, even such a simple thing as a phone book, here with some made-up names, Alta to Zyström, is impossible to maintain if you have to rely on prints, or if you don't have a web. Because you can imagine some researcher goes there and people tell them, here's your office, there's a phone, you can talk for free within the building, and then his phone number is 234. Until this is in print and distributed somewhere, he has already left again, right? So it's basically, it does not scale. So no one can call this poor person, even if they know that they are there. And in 1989, even if you cannot imagine this anymore because some of you were not born, there was no such thing as a mobile phone for normal people. So they were unphoneable, you could say. And then Berners-Lee had the idea to say that, well, rather than instead of having this phone book, we want to put this phone book on an infrastructure that was already known, which was the internet. Well, internet and TCP/IP was already known. What is the internet? As the name says, it is a net connecting different nets. Right? For example, you may have here one system that's built on Ethernet and connecting several servers. And at that time, that might have been workstations based on Unix. Maybe there was another net for some mainframes, with some mainframe system different from Unix. 89, maybe there were even there was even one or the other personal computer with some novel network, a token ring, other kind of network. And TCP/IP was allowing to communicate over these different networks. And how would you communicate over these different networks? It was very easy. You had this black shell. You memorized 50 different acronyms for connecting. You memorized how the names of the servers were. Okay, the domain name system was already invented. You don't have to memorize the numbers for the servers anymore, but you had to memorize the acronyms and for the commands and the server names all in your head. Then you would write on black shells some of these cryptic commands. Please don't mistype anything. And half an hour later, you were on that other system. Right? And then you could, for example, put something on this other system, like a telephone book, or do a lookup of what the telephone book said there. Obviously, that's not so nice if you're not very good at memorizing things. So he had the idea to say, yes, we want to use this great infrastructure, but instead of having one phone book, and the phone book has even the problem, it still needs to be updated, let's allow everyone to provide his data on his system. So if you're on this system, maybe that green thing is your web page. If you're here, maybe that blue page is your web page. And let everyone provide his data, his text, his phone number, his hobbies, on documents as he likes to do, or she likes to do. And then, you know now what comes, because you know the web. We do not just have isolated documents, but we have hyperlinks that allow you to go from one web page to the other web page. So you can have one index that says, here are these people. In order to get the telephone number, please look up the web page of Züström. He can write up his telephone number there if he cares. And the interesting thing there is that the technology was all there. The technology idea had been invented 20 years before and more. But putting this up and having this work socially, that was the great invention of Tim Berners-Lee. He invented a simple protocol, HTTP. You still find it in the URLs of your browser. And he said hypertext transfer protocol means that you take this document, you parse the links, and when you hit one of these links in your browser, you load this other document across different networks. So the kind of web that Tim Berners-Lee invented basically said, we use documents with hyperlinks, that's called hypertext, and hypertext dated from the early 60s. So already then it was more than 25 years old. We take the internet because the internet allowed us to use TCP/IP to implement our hypertext transfer protocol. And very importantly, we use this social phenomenon that we give the power to the people to provide their own documents, to provide their own web server. So you don't have to rely on someone else to do work for you. And why is that so important? Let me cite from my own experience. I was once working as a consultant, And I was working as a consultant in an insurance company, and we were supposed to develop something for the insurance company. It took 2 months. It was in Germany, so we're very careful. It took 2 months to let me into the system while I was there full time. And obviously, because I could not just sit around 2 months not doing anything, I was giving the credentials of some other person, which of course completely destroyed all the reliability of the security system for 2 months. But you could not wait for 2 months not letting the people work. With this kind of system, you let people work in an autonomous way. And that's the power of the web. You can put up your next web server and put stuff there. And you don't have to wait for anyone. And then you have these dynamics. If you make something wrong, no one else cares. Maybe people come to your website and they don't come again because you did it in a crappy way. But that allows people to explore things and to do it independently from each other. And that generates the innovation. That accelerates the innovation. Because people can do it independently, you are open to innovation. So the web that Tim Berners-Lee invented was technically just hypertext plus internet plus a few protocols to do this in a simple way, plus allowing all the social phenomena. So he was knighted for that. 1 billion users later, now we have more like 2 billion users, 2 and a bit billion users. But then a few years later, and already very early on, he had not only thought about documents, but he thought about data. And he asked himself the question, if we do this for documents, why should we not do it for data? Why is data so much different than documents? Is there a good reason for that? In a way, documents, you could say, are more complex than data, because a person has to sit there and read the document and understand the implicit semantics. Here we have it again, the implicit semantics. So, and he had the idea to say that now that we have these colleagues like Systrom and Alta, and they have these telephone numbers on the web page, isn't that a waste of efforts? I have to go there to understand that there is this telephone number. How? If we try to collect these telephone numbers from their web pages and put it in a kind of central telephone repository. So we leave the autonomy of providing the data to them and organize a collecting process. Okay, the problem with that, of course, is the implicit semantics. If you think of to a computer, the web pages, the green and blue things here, up there, they look like this to me. I don't speak Chinese. I don't even know whether it's Chinese or Korean. I think it's even like the sites switched. But it doesn't matter to me anyway. And it doesn't to the computer. Because the computer, it doesn't matter whether you give it in Chinese or German or English. It's all non-understandable garbage to the computer, more or less. And so Tim Berners-Lee said, okay, we can work on natural language understanding, and it works to some extent. It often breaks. What if we do it in a simple way? It's not so difficult for people to say, here's a telephone number. It's probably easier for people to say, here's my telephone number, than for a computer to understand that this is the telephone number. So when we allow people to say that, to mark up a piece in the green document as a telephone number, then we can just pull this piece of data from the green document into like a kind of central repository. Before that, we only pulled whole documents into our search engine. And now we pull pieces of data into our repository and have it as data. What do you need for that? Well, of course, you need a language to describe data. In the web, we have HTML, hypertext markup language, in order to understand hypertext documents, to understand what a link is, to understand what italics is, and to understand what a heading is. Here we go one step further, not just describe what a heading is, but we go to a language that allows you to describe what a telephone number is. Well, then you do not only need to understand that there is a telephone number, but maybe that a telephone number is a sort of an address to reach someone on the phone. So you need a language to describe the schema, not only the data itself, but the schema. You may need to understand that a mobile phone number may look a little bit differently than a landline, for example. And then, of course, you need the exchange of data and schemata via the internet. Okay, we used the internet before, so we use the same kind of protocols as before. And actually, people who look at the semantic web, they still use HTTP a lot. And you need the social phenomenon. You need lots of people and applications. So the semantic web is semantic web data, like the markup of something being a telephone number. You need schema descriptions, we call them ontologies, to describe how a telephone number is related to a person, for example. This is explicit semantics, by the way. You need the internet for shipping around the data. And you need the social phenomenon. And 20 years later, what we have is this linked open data cloud as a part of the semantic web. That's not the whole semantic web. It's often used nowadays to describe that there's a lot of data out there on the web described in the semantic web formats. And what are the domains that appear here? There's a lot of happening, this is green thing here, around publications. So you have descriptions about authors and papers they have written. There's a lot here in the medical domain. People in the medical domain love this kind of data because they're really open to sharing data, right? I mean, they want, many of them, not all of them, many of them want to take a profit by storing data away, but many of them want to share data because they want to help save patients. There's a lot in the geographical domain. I think that's this area here, where you have information about where is Lisbon, for example. What are the geocoordinates of Lisbon? And so you have this data now on the web, about 30 billion triples, where a triple is like the smallest entity that you can have. It's a fact. It's describing, for example, that Lisbon has geocoordinates x, and then comes the x coordinate, and it has the y coordinate, and then comes the y coordinate. So you have triples like this. And now, of course, what is the semantic web in action? What are examples for that? And I want first to show a few applications that we did, and then some, I would say, the really successful ones that are done by major providers in the web. So what is one kind of application that we built? It has been called Lisa. You can still go on the web and check it out. And here it's about Munich. And this kind of application, it collects data provided by the town of Munich, provided by OpenStreetMap, provided by GeoNames. And you can then look at areas in Munich that are interesting for you. What are interesting areas? Well, that depends on what you are. If you're a family with small children, you may be most interested to have schooling and kindergartens nearby when you look for a house. If you're a business person, maybe you're more interested in having a lot of traffic that can flow by, park for your shop, and then buy something and go away again. So what is important for you depends on what you want to do. Do you want to open a business, or do you want to find a house for your family? But you have this data provided by the city and provided by other partners, and you can aggregate this data and do a nice map of how the city looks for you when you care about certain data. And we were even a bit successful, like winning a certain competition. Another example, Web 3.0. What did we do here? We wanted to explore Flickr content. For example, this here is an image of the Koblenz fortress. And you find, of course, many images of all kind of sites on Flickr. And we were interested not only to find this kind of images, but we wanted to understand the context. And what is the context of these images? Well, on Flickr you have tags. So in order to look at Flickr, we connected the API that Flickr offers you and the tags that they allow you to search for. But we also looked at knowledge, for example, from DBpedia. DBpedia is a kind of database version of Wikipedia where people from the semantic web community try to scrape facts into a kind of database format, actually also in the same kind of semantic web format that I talked about before. And then you do not only know something about coplans, as I will show you in a minute, but you will know that there are several coplances out there. You have persons that you find by looking at data on the web. You have links, you have geonames, which gives you more information about a location like Coplands. And of course, you have OpenStreetMap again. So we visualize in our tool where you find certain images. So let's say you start in some place. That's a snapshot I did in Nice. And you look for Coplands Castle. And first, what you're offered here on the upper left is Coplands or Coplands Switzerland and Coplands Hauptbahnhof. So I'm from Germany. So there's another Coplands in Switzerland. And if you book a train ticket, be aware of where you're going. We had visitors that ended up in the wrong place. Right? So you really want to understand that these are not all images of the same location. Then if you choose Coplands, you get an OpenStreetMap and you see where you find certain images. This gives you information about where are the sites. For example, here, here this is a very touristic site and you find many images there. And here is the old town, so you have more images there than in some of the other places here, which is okay, but just a living area. And once you have here Coplands, then you have also further knowledge from DBpedia, from Wikipedia, what Coplands is, how it was founded, and so on and so forth. And you have information about specific categories. For example, here about the fortress that you saw on the picture before. And then you can look for this fortress and see some picture today. And you can look for other tags. And so you can really explore not only the image, but you see the whole knowledge that's existing around this sort of image and around this geolocation. And you can go into persons, and you find that a former French president was born in Coplands, and so forth, and we also want some competition with that. To go into a completely different direction, when you look into science and medicine and bioinformatics, at the time, it's already like 2 years ago, so when we built this kind of system, there were more than 1,000 databases registered with a certain bioinformatics journal. When I talk about 1,000 databases, some of them are smallish, maybe just thousands of facts. Some of them are huge. Some of them are pay for access databases. Some of them are completely open. And for a bioinformatics person, for a researcher to work there, the person has to connect different databases. Now, connecting different databases is really tricky because you quite often have independent access to them. What is now standard is that you have one information retrieval interface to many of them. So you put forward a search term, and then you get the individual results from these individual databases. But what you really need is the connection between them. You really need to understand how a substance is composed of molecules, what kind of properties these molecules have, whether they can participate in a chemical reaction, whether this may trigger some biological reaction, and so on and so forth. So you have a database like this one, and that's KEK. And the interesting thing about these databases is that they give you a lot of structure on the outside. For example, you have here these nice HTML pages, not very fancily layouted, and they tell you rather precisely what it is. You have here some entry, which is this acronym, which is a compound. And it has a certain name and a certain mass, and it participates in certain reactions. The funny thing is, on this web page, you have this in HTML. If you look for the database, it's a mess. If you look at the database, it's very hard to understand what's going on because it has been developed by biologists They don't have a clue about normalization theory in databases, and it's just a mess. What they cared about was that the output on the front end of HTML was nice looking, so people would understand what it is about. So the output is not fancy, but it's well understandable for the biologist. And so what the challenge then was to really look into this and extract the connections, you could say the RDF structure, among these different enzymes and reactions and other enzymes, and how this all works together. Okay, these were some examples of works that we did, and these works were about using explicit semantics, given, for example, by the town of Munich, for looking at their data and at the data of other people and making it understandable to people. The second example with Flickr was taking some explicit semantics, but also letting people explore the implicit semantics that's in there in images, that's in there in maps. And this one here has only implicit semantics. It has no explicit markup at all, but you can extract some formal structure that something is a compound, that something is an enzyme from it, and turn it into something where you can query for it, where you can combine it with other databases. Now, let me look at some of the really sort of now famous applications that you find on the web, not as research prototypes, but as real working versions. And that's like the huge scale version of the semantic web, you can say. What happens when you Google for Vincent van Gogh? Of course, what you still get here are these kind of document, is this document view. You get a document about Vincent van Gogh. But when you actually look, you see that there is a lot of structure about Vincent van Gogh on the web. For example, there's a Vincent van Gogh website on Facebook, right? And the Facebook site of Vincent van Gogh or about you is not just text, but when you look up there, you enter your birth date, for example, if you want, or your address and stuff like that. So it's a lot of structured knowledge. Here there are photos, and the engine knows that it's photos and that these are have a certain quality and things like that. You can actually use the API of Facebook to look at the data that's lying underneath. And you can use the Facebook API to get out concrete data about Vincent van Gogh from the Facebook webpage. You can also look on Wikipedia, and actually, especially in these info boxes on the right that you have, for example, for persons, you find that there's a lot of almost structured knowledge, for example, when the person was born or when the person died. I say almost formal because it is of different quality. For some people from the past, you don't know exactly on which day they died, or you don't even know exactly the years in which they died or in which they were born. So it's not precise data. And there are people who care about it to turn this kind of semi-structured knowledge into structured knowledge and provide this in RDF and in different languages, like is done in DBpedia. And Freebase is a company that has been doing this for a couple of years and has been bought by Google in 2010. Right now, we are working together with Microsoft, and Microsoft is working on a similar system that they call Satori. I know that Hewlett-Packard, HP, they're working on collecting such kind of data for years. They all work on collecting explicit semantics from these data sources and turn implicit semantics into explicit semantics. And what you get with when you do the Google search nowadays with Vincent van Gogh is not only the document view, but you get also the Google Knowledge Graph view. And Google has announced that it's the Google Knowledge Graph that they harvest from Freebase, from Wikipedia, from other sources, is strategic for them to enrich your search experience, to get not only documents, but directly data where you learn, for example, about birth date or death date of such a person. Another famous application is schema.org. Behind schema.org is actually a kind of invention from Yahoo. That was called SearchMonkey at the time. And what you now find behind schema.org is Yahoo, Microsoft, Google, and Yandex. Yandex is a Russian search engine provider. They have agreed on certain ways to write down semantic data explicitly in order to improve your search experience. How do they do that? You can see that when you go to Google Rich Snippets tools and you look at a web page like the IMDb web page, and you can look at a particular one like Men in Black. And when you provide this web page to Google Rich Snippets, it analyzes the formal data that's given by the Internet Movie Database IMDb, and it shows you the formal data in this kind of structures. So what you find in IMDb is not just the running text or the HTML tables, but there is information about what is the data in IMDb as explicit metadata. So I described to you these telephone examples. You could say they're applying this telephone scenario to their movie descriptions. And you find that for Men in Black, for example, the title is Men in Black. They say what the type is. It's a video movie. They give unique identifiers. They describe here that it follows a certain schema, namely the schema.org. That's the kind of like agreement that the search engine providers have about how to describe movies, for example, or other kind of products. Here they describe a movie. And movies have certain type of properties. And here you aggregate some stuff, for example, the stuff about who is the director, who are the actors, and you get quite an elaborate database view about this movie Men in Black. So basically what they do here in IMDb is they're opening up their database for you to take advantage not just of the document text, but of the data lying underneath. And in schema.org, you can do this using this established vocabulary for all kind of creative works like movies, but also for events, for organizations, for products. There's now a product ontology called Good Relations with several tens of thousands of concepts where you can describe your products in a formal way, in an explicit way. And I'm not quite sure why IMDb is doing that. I like to use this example because it's easy to understand. There is some return on investment, and the catch is the following. When the search engine provider understands what is on this web page, it gives you a better summary of that web page. And if you get 10 search results, and for one search result you have a better summary than for the others, the likeliness that you hit this search engine result is increased. And therefore, more people hit this web page. If more people hit a particular link, the search engine providers assume that that's more relevant, so it receives a higher ranking. So people or companies that use that kind of scheme get a better placement in the search engine results. And Best Buy, that's a provider in the States for electronic gadgets of all kind. They reported a 30% increase in traffic to their pages. They were very early adopters of this mechanism. Yeah, and there were some other numbers provided by Yahoo that they reported a 15% higher click-through rate and stuff like that. And that, of course, means immediate money for the companies that want to sell something. There is still quite a challenge in there. And why? Well, if you look at movies, like IMDb, you find that some properties are always used. Like in movies, in 78% of the cases where the movie type is used, also the title property is used. At IMDb, it's probably 100%, but some other sites use the title only 78% of the time. The actors appears only 38% of the time. So what you see is that people who provide this data independently, of course, do not fill out very carefully all the different fields. And you can produce something like this matrix where you look at certain entities, like a particular movie. Does it have a title? Does it have actors? Does it have a director? And you end up with a matrix like this where certain properties are used, certain properties are not used. That looks a lot like the implicit semantics analysis that I described to you before. We now have formal structures, but we understand that not all properties are used all the time. And then if we start to search for a movie, we also don't get 100% precision and recall, because we have formal structures that we can use, but we have new challenges that arise by people doing this as a social phenomenon. And people who do this, who contribute, they don't work like machines. They do mistakes. They give you more information than you had before, but it's not perfect. And for example, when we want to retrieve all movies, it's not good enough to ask for all the movie types. You also want to ask for certain combinations of properties. You want to ask, let's say, for title, description, URL, and director. And this gives you a 78% precision and 26% recall. So when you ask for these 4 properties together, what you get back is in 78% of the cases correct, but you miss actually 26% of all the movies. So asking for a movie is still not simple, but what you get is more explicit than what you got before. And in our lab, we also looked at this problem, and what you also see is the patterns, how people use explicit semantics and implicit semantics varies from source to source. So in DBpedia, you have a lot of explicit types, more than 1 million types coming from DBpedia. So movie is one type. There are more than 1 million other types like this. You probably find something like Portuguese movies shot before 1920. Yeah? It's very likely. And you have 1 million types like this. You have properties and property sets. A property set is a combination of properties. And you find a couple of 100,000 of property sets. So you have in DBpedia more types than property sets. It's different in some other sources in Freebase, which is more curated, and so you have other kind of ratios. Okay, so I think I've come to an end slowly, so I jump a little bit over one activity. We went from the consideration of how to look at the world and look at facts, from a long history in philosophy, making up logics, engineering data, engineering computer programs, all having an explicit semantics. We found that we could not apply this in all circumstances, for example, doing web search, where we don't have an ontology for all of the web. We have the implicit semantics where web search engines look at co-occurrences of words in order to give you meaningful search results. The semantic web departed from the idea that you decentralized the document creation process first, and then the semantic web idea was to decentralize the data creation process, but providing this in a format that makes the semantics rather explicit. So it is a kind of democratization of this modeling process, which before was done in small software producing entities, and gives it back to everyone. And you see some of the power of that, for example, also in medicine now. ICD-11 is a standard for classifying diseases that's used in every ambulance in all Western countries. ICD-1 to ICD-10 was all done in a centralized fashion by specialists working on this taxonomy of diseases. ICD-11 is not done in this way anymore. ICD-11 is done by all the people concerned on the world, It's done in crowd-working fashion. Ambulance drivers may contribute to ICD-11, the new classification of diseases. The semantic web is also this kind of decentralization of data. And this gives us a lot of explicit semantics with some of the advantages. But when we look at it, we see some of the implicit semantics coming back at us and giving us new challenges because we don't fully understand yet how to combine these advantages of explicit semantics with the challenges we receive by giving this process out to all people over the world. And of course, it's not yet like 2 billion people who produce content in this way. It's growing, but not at that exorbitant rate as the web did. But we see from stuff like schema.org that it makes a difference to the business of people. We see from bioinformatics that it makes a difference to what people can do for research in this field. We see that with Google Knowledge Graphs, it gives you a richer, explicit search experience. Now the challenge is up to you to, well, define the next business on that, or to solve the next research challenge, to reconcile this between the explicit semantics of semantic web structures and the implicit semantics of what people give back to you. And, of course, it doesn't end there. We have new devices, new ways where we can observe things. For example, in Koblenz, we look at cognitive phones, smartphones with sensors, and trying to make sense of that. We look at eye tracking, trying to make sense of how you collocate semantic search with eye tracking and trying to derive the meaning of what you find. And, well, maybe you are interested to join us in our research. We always look for bright people, of course. And thus I can conclude, but I'm very happy to take questions, discussions, and you can also say that, well, everything I said is wrong, but let's engage in some discussion.